All right, and with that, Rujna has a few words to introduce
Okay,
our guest.
so I'm Rujna Baichi. I'm sure everybody knows me, but anyway, just to make sure that you know that I'm alive. Some people ask, considering the situation. It's my really pleasure to introduce Camelia Taylor, who is a professor of computer science. You are in computer science department, correct? At University of Pennsylvania in Philadelphia. CJ, as we call him affectionately, is, in addition to being a professor, he's also an associate dean for underrepresented population. But CJ did his undergraduate at Harvard in 1988 and MS and PhD at Yale 1990-94, and that's when I discovered him and met him and tried to court him. I was at that time a chair of the computer science department, and I thought, he would be a good person for Penn. But he eluded me and went, and first he had a fellowship at Harvard, but then he went to Berkeley. And with whom did you work at Berkeley?
Oh, I had a chance to work with Jitendra and
I see. Okay. So anyway, he was at Berkeley for 2 years, and then finally I convinced him to come to Penn. So he joined Penn in 97, and this was the time I left for NSF 99, so we kind of overlapped for 2 years. He's a superb teacher. I mean, you can really only admire him. He got various awards for teaching, but he also is a very good kind of combination of theory and engineering. And Vijay Kumar told me that, without him, a lot of these projects that they get from DARPA and Army and NSF that would not work if it wouldn't be for CJ. So right now, he's going to be the general chair at ICCV, which is the International Conference of Computer Vision. Some of you may know or not know, and I see here Jitendra, and he will be the general chair in 2021, which is next year. Hopefully it will be Yale. And today he will give a presentation on robust three-dimensional slams. So welcome, Camille, CJ, and thank you for agreeing to talk to us.
Oh, thank you, Rujna. It's always a wonderful opportunity to be able to come back and meet some
touch base with some of your old advisors like Jitendra.
People to whom I owe so much. And actually, I've been going around to all of the department meetings lately and actually telling them the story of how I ended up at Penn, because so many years ago, Rujna Baichi knew who I was at a conference, and that made the entirety of the difference. So thank you very much for everything.
Well, it worked out for both, for Penn and for you. Great.
Okay, well, let me try to dive in. I'm going to go ahead and share my screen if I can.
I think you should be able to. Let me know if you have issues with that. Okay, great.
Okay, so is that working?
Yes.
Okay. Well, all right. Okay, first off, let me go ahead and apologize in advance for the vagueness of my title. It's one of those, again, situations where I'm trying to fit a lot of different things under one talk, which means that I probably have hopelessly too many slides and will probably not do as good a job as I should on each of them. So please, stop me when I'm rattling off incessantly. The brief outline of what I want to talk is just talk very briefly about some of the motivating projects that we've been involved in here at Penn, and then use that as sort of a little bit of a springboard to go on and talk about some specific things that my students have been involved in, trying to tackle various pieces of this 3D perception problem. So let me, again, just sort of jump right in and talk about a couple of the motivating projects that we've been involved in. But before I do that, let me again acknowledge that the people who sort of do all the work around here are, of course, our wonderful team of students and postdocs, many of them pictured here. We got to all work together on a project called DARPA FLA, which is the Fast Light Autonomy.
What? Hi, how's it going?
I'm going to take your card.
FLA was all about building completely autonomous aerial robots. So the idea was, of course, to put all of the perception, all the planning, all of the smarts, if you will, on a single platform and sort of send it off in the wild. So this was something that kicked off around 2016. This is one of the platforms we were working on then. We call it the Falcon 450. It was 450 millimeters from one propeller to another, to give you an idea of the scale. And this was equipped with, in this case, a pair of stereo cameras, an IMU, in this case, an onboard LIDAR, and all the computation happened on board Intel NUC. So to give you an idea of the kinds of problems that we were interested in being able to tackle, the way that DARPA had it set up is that you would start on a particular point and they'd give you a range and a bearing to where they wanted you to go. And that was it. So your robot either made it there or it didn't, and there was a loud crashing sound. You are not allowed to look at the environment ahead of time. You just have to launch and let it go. So this is, again, a pretty our approach to this had many of the components you would usually expect. There is a component that's involved with maintaining the position and orientation of the robot, sort of in a global frame of reference. And this was done using a stereo visual inertial odometry system that we came up with. That was used to help us build a map of the environment. And that then was coupled with a planning algorithm, which was used to try to reason about approaches to getting in and out of spaces. So this is our robot sort of interrogating this structure. And so far, it's not been terribly lucky in terms of finding a path to its final destination, which is somewhere here in the center. But this robot is a hopeless optimist, so it's going to continue along, continually refining its path until at some point it finds some way, hopefully, to get in, or its battery fails. So this was a Air Force base at some undisclosed location in Florida. Tremendous number of alligators, which was a lot of fun. So once you get inside, of course, you have to deal with this problem on the interior as well. Navigating around until you figure out find what you're looking for, and then you turn around and you do it all again in reverse. So this is kind of one canonical example of the kind of standard sense, plan, act loop. We've continued in this vein. So this is sort of an evolution of this same kind of project where we were starting with this 450 millimeter system, but our program manager decided that we really wanted to get down to a smaller size platform. So we were asked to get basically halve the size of this. We were given somewhere on the order of 6 months to do so. That was a bit of a heart-stopping moment because having the size has a lot of consequences, as you could imagine, for what you can carry on board there. So we actually had to rethink and do a complete redesign of the computing and sensing system. So this led us to the following platform. So here's a 12-inch ruler for scale of what we were able to get down to. And the reason we were able to do so is that we custom designed this unit here we call the Open Vision computer. And on that, we integrated our pair of stereo cameras, our IMU, a field programmable gate array, and our NVIDIA TX2. So we did all of the sensing, all of the inertial sensing, all the time stamping, synchronization, low-level feature processing, and the complete autonomy stack. On this unit, it was a little less than 20 centimeters, it was a little less than 200 grams, and a little less than 20 watts of power. So all of those numbers were kind of important in order to get down to this size and scale factor. So there's a lot of hardware-related issues, which I'm going to restrain myself from delving into. But there are, other than to mark that, there are some very fun things that you can do when you have better control of your hardware that we were able to take advantage of. So the reason that we were being asked to get down to that size and scale was that the project that DARPA had in mind for us looks something like this. We wanted to have these kinds of missions where we would start outside of a building and then be able to send the robot up to a system, have it recognize a window and enter it. And then once it was inside, be able to do a full building explore. So actually a lot of the dimensionality came from the size of that window. It turns out that getting through that window, we had somewhere on the order of 2 or 3 centimeters clearance on either side, given the dimensions of our system. So we had to actually be pretty accurate in this case. The system in this case is actually completely autonomous. It has no prior understanding of the environment. It goes around, and in a normal course of events, it would actually explore the rooms, but to keep this video short, we elided that part. It's also keeping an eye out for staircases. So here it sort of detected a staircase, and it's going into its stairway descent mode. And after doing stairway descent, its goal in life is to simply get out. So that's what a typical mission would look like, and just a little idea of what the robot's eye view of the world would be in this case. So again, the primary sensor is a stereo pair plus IMU, but we're also equipped with in this case, with a depth camera that we could fit on, and that was helping us to sort of build 3D maps of the environment. The purple is a planned path, and that planned path gets updated as it learns about the obstacles in the environment. And in this case, it's going to go in, it's going to explore rooms and go through doorways and the like. So clearly, in examples like this, 3D perception is sort of one of the key things that enables this kind of operation. Though there are other ways that we could approach it, but in part, one of the things that we want to get out of this is an accurate 3D map. So once this thing concludes, you'll sort of get a sense of the size and scope of the maps that were built. Okay. So just to give you a quick, so while this was actually being sent around in indoor environments, the last day of testing, our program manager turned to us and asked us to try it out in this situation over here. That's always fun, but since he's the guy with the checks, we do what he says. So this is a similar kind of idea, but through a completely different environment. This was a lot of fun because it turns out that in order to go into this building, you have to be Rubble certified, and none of us were. So we were told that if we crashed, that's where the drone would stay. So it was a good thing to try on the last day. And thankfully, we didn't lose any drones. So I'm going to mark that as a success. I'll also point out that none of our pilots were comfortable trying to navigate through these kinds of spaces, but our code is super stupid, so fools rush in where angels fear to tread. So this was
I had a quick question. So You said that you didn't crash in the rubble scenario. Did you see any interesting failure cases, or did it just work?
We were super lucky. It kind of just worked, actually.
Nice.
I mean, the failure case, if you want one, is that our drone was like really happy getting very close to things, much closer than our human operator was interested in doing, which you could see as kind of a failure case, but in this case, it kind of worked out.
Cool, thanks.
So CJ, since you have the destination, so the main thing is obstacle avoidance here, right? And you build maps along the way to help you with obstacle avoidance.
Pretty much.
The primary challenge is obstacle avoidance, is it? Or
yeah, and the planning associated. There's a lot of the stuff that I'm leaving out here. So there's actually a whole bunch of research we do on, because this is a platform that essentially can't stop, you have to do this planning in a very, in a dynamic sense. So there's a whole slew of work on motion primitives and how we integrated that into the map and the like, but I'm saving you some of the hairy details. But yeah, but essentially it's keep track of where you are, figure out where things are, and then create a flyable plan that gets you to where you want to be. So
the tricky thing, suppose there was like a maze.
Yes.
Okay. In that case, the planning has to be strong enough that it can solve the maze effectively.
Yes.
So the maze will be there only. The maze will be built up partially, right? The maze will be built up as you are flying.
Exactly.
You have to be solving the maze.
Exactly. So that's kind of why I showed the first one, and there are many others of that seam. So DARPA, because they're evil, literally inside they would create mazes inside the building, and they wouldn't tell us about it. So you had to go in and you had to go down, and if you went through a blind alley, you'd have to remember, you'd have to go back, and you'd have to replan. So it actually had to solve the global planning problem in this case, and not just obstacles avoidance.
Got it. And the maze could be simply connected or multiply connected, and
Yeah. There were even cases where they could change the maze a little bit if they wanted to.
Okay. Got it. Thank you.
Great. So let me, so that sort of gives you a taste of sort of some of the things that we were interested in. And I want to sort of take it in various ways that things that came out of some of that thinking. So one of the things you observe is that for indoor environments, this idea of sort of building very, very complete pointwise voxel models always seemed like overkill. And not only is it overkill, but it seemed like we weren't really taking advantage of what we knew sort of structurally about our environment. So there was a tranche of work I did with my PhD student, recently graduated, Arman Shariati, on something we call Occam Slam. And the idea in Occam Slam was that we were interested in building parsimonious models of buildings and taking advantage of sort of structural regularities where they exist for two reasons. One, to actually increase the accuracy of our model and and consequently of our trajectory estimation. But secondly, what it allows us to do, as I hope to convince you, is actually fill in places that we haven't been. And use that instead of flying all over the place and sticking our noses into various nooks and crannies. So our first thought is kind of structural slam, is that what we actually want to do is build a model that starts off with infinite planes being a fundamental primitive. The second thing that that's interesting about this work is that not only do we use that, but we also combine this with a model selection piece, in that we're interested in coming up with simple models of the building, sort of the simplest model that explains our available measurements. And we do this through a canvas optimization problem that we can actually solve efficiently online while the robot's moving around. And we actually fuse this with the data association. So I'm going to try to cover that in a couple of minutes. So let's start out with a simple version of this. So let's imagine that we live within Manhattan structure. We generalize this, but this is sort of a good place to begin. So in Manhattan structure, what we think is that the dominant structure is laid out along two perpendicular axes. Let's call them north-south, east-west. So given that, there are actually very simple real-time techniques that we can use to sort of keep our orientation with respect to this dominant structure. So we like to use something we call a entropy compass, which again, we can run in real time, that basically involves interrogating the entropy of the points around us. But basically you can think of it as a compass that tells us where we're oriented with respect to things. Given that, we are able to do a plane extraction. Again, this is a relatively simple operation. So here we see points that are being returned from our 3D sensor being coded into green and red, corresponding to whether they're X walls or Y walls, along the X-axis or along the Y-axis. So the end result of this is that we can think of our robot flying around as getting two different kinds of observations. So one observation is a compass measurement, which allows it to align itself to the dominant structure. And the second set of measurements are measurements to walls, X walls or Y walls. And it might see 1, it might see 2, it might see 3, it might see none. The third kind of measurement is a measurement that sort of links subsequent positions to each other. So you might have a situation like this. So yeah, X walls, Y walls, camera positions, and so on. So this, of course, sets up like a factor graph, where the black nodes correspond to robot positions, and these measurements to the squares and circles correspond to measurements to these planes that we're measuring. And a measurement basically consists of distance to the wall. And of course, your orientation is already solved by your compass. So one way to do this is to just form this graph and solve it using your favorite factor graph solving techniques. The extra thing that we do is what we're interested in is actually making associations between wall segments that are seen. So what we want to say is that the wall segment seen at this time over here is the same as the wall segment seen as at this time. They're not two separate walls. Now, the issue is that this can be a really, really strong constraint. So imagine that you're walking down a very, very long corridor. You might have a structural wall, but it looks very, very different. It has different color, completely different features as you walk along. So there may not be anything that immediately tells you that there's like a common feature or something that does this. But if you can establish that it's in fact the same wall, that powerfully constrains your position. So the way that we think about it is that we hypothesize relationships between these wall fragments. So these are indicated by these dotted lines here, and so on. And then we're basically going to try to figure out which of these hypotheses are correct and which of these are false. And we're going to fit that all into a convex optimization scheme. So in our system, we have two kinds of measurements. They're measurements that relate camera positions to each other. So position at time I+1 and position at time I, and they're related by some translation, let's say. And they're positions that relate the camera position to the wall position. So these are model parameters. So model parameters associated with X walls, Y walls, and Z walls. And these measurements are in the form of when you were at camera position I, you thought you were observing wall J of type X, and there's a distance that it should be. And these are all very, very simple, highly linear measurements. So one way to think about what's going on is that in a traditional way of thinking about factor graph or bundle adjustment would be to think about it as minimizing some sort of L2 norm. So this is a norm that measures the discrepancy between our predicted measurements. So here's our model parameters and our camera poses. And here are the measurements that we're getting. So the distances to the wall and our translation measurements between the camera poses. Now, on the other hand, we have these proposed constraints. So when we say something like this wall that I saw at time 7 is the same as this wall that I saw at time 10. Those constraints take the form of these homogeneous linear equations, like so. So these are constraints that relate x walls, constraints that relate y walls, constraints that relate z walls. So we think of this as an equivalence system. So we denoted by this matrix E, and our constraint is of the form E psi is equal to 0. Now, what's happening is that we're actually not sure which of these constraints pertain and which of them don't. So our model selection process is really going to all be about which of these are actually 0 and which of them are not. So ultimately, the way that we tackle this problem is as a sort of a relaxed convex optimization form. So the question we're asking is, how many of those constraints can we satisfy, given that we want to bound the amount of error that we observe? So we want a solution to our model parameters on our poses that is consistent with the data. So that's what this constraint is saying. And given that, we want to ask, well, how many of those putative constraints could actually be plausible? So this is what I would really like to be able to do. So this 0 norm is, of course, not so friendly. So we use a standard technique and relax that to an L1 norm. And then this becomes basically it can be seen as optimizing a L1 norm subject to an L2 norm constraint, which is something that can be solved quite efficiently, even when we're talking about very, very large systems, because the resulting systems are so very, 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 very sparse. We can throw weighting into this formulation extremely simply, just by, in order to reflect prior models about belief. But the bottom line is that we are able to then construct models that look a little bit more like this. So these now green and red are the infinite planes that are recovered automatically by this procedure. So again, the system simply hypothesizes constraints and then throws them to the back end, and the back end makes a decision for which of these constraints are plausible, as in it tries to come up with the simplest model, as in the one with the fewest number of planes with the maximum number of equivalences that is still consistent with the data that we're providing. So this has an extremely salubrious effect on our solutions. So both in terms of increasing metric accuracy by enforcing constraints, but also in terms of improving the accuracy of our resulting trajectory. The thing I would actually like to sort of point out on this table is exactly the size of the problems that we're able to consider. So basically, we throw the kitchen sink at this thing. So these are different examples of problems where we're throwing 10,000, 15,000 possible equivalences. And it's able to actually extract quite a lot of this regularity. And we're able to run it in a reasonable amount of time. And the result is that we end up with very, very parsimonious models that are actually quite accurate and are able to do it quite well, in fact. We can obviously extend this basic idea, so we can have more than just 2 directions, and we can include z directions as well. I'm going to basically elide this, but there are other aspects of this that allow us to marginalize out variables, which is important when we're talking about systems that need to run for a long time. But sort of just to give you a flavor of what this might look like. This is a run where as the system goes through, you'll see it sort of establishing these planes that it's automatically discovering and using those planes to understand the structure of the scene. This is, of course, this is done in real time, by the way. So this is a process that we can run on a real robot. I guess I'm going to skip ahead and just in the interest of showing you this other one. which is, and the reason I wanted to show you this one is that this is in full and glorious 3D. So if you've ever been to Philadelphia, and Rujna will know this, we're very fond of thin, narrow houses that go up 2, 3, 4 stories. So what I'm showing you here is this automatic plane estimation scheme run on a multi-story building. So we're not just extracting planes along the X and Y direction, we're also extracting them at these odd angles and extracting them in the Z direction. So at the end of the day, we end up with a map of all of these structural planes that also is helping us to constrain the way that we reconstruct the system. And we're just showing the point cloud a little bit at a time so that you can get a sense of what's going on. All right, let me move along. The other point I want to make here is that these recovered infinite planes, not only they're sort of good for actually helping us estimate where things are, they also provide us a basis for partitioning the floor space into regions. Because now we can talk about the convex cells produced by the slicing action of each of these planes, and then talk about putting them together in various ways. So to give you a sense of what that looks like, what we do on top of this is not just extract a 3D model, but we also then try to go back and infer what the actual semantic structure of the world looks like. So in this case, we want to divide the world up into corridors, which are purple areas, rooms, which are these kind of magenta-ish areas, and doorways. And again, you can imagine that for those of us that are thinking about robotic applications, this kind of level of representation is something that we kind of aspire to sort of think about the world at a slightly higher level. So again, this is now with this kind of semantic analysis applied on top of this, one way to think about it, this gives us an automatic way of extracting kind of the overall scene, the structural elements, the walls, the doors, and stuff such like, and then we can go in and start talking about furniture or other kinds of objects that we might be interested in gathering. This is simply here to point out the various analyses we did of accuracy, which is pretty good in this case. And the other, I guess, final point I want to make on this is not only are we sort of able to sort of extract out environments that we see, and I think importantly here is that by asking the system to produce these kind of convex regions, we're able to actually start with partial data. So you might be in a situation where you stick your head into a room and you only see like 1 or 2 walls, but the overall analysis allows you to infer the size of the room that you're in. And that saves you time in terms of not having to actually go and observe every last corner. The other thing that you can do is you can speculate about places that you haven't been, because you can use the structure that you've detected and you can extend it in various ways to propose possible corridors or possible rooms, which could then be explored or verified by subsequent experience. Okay. All right.
I think Rujna had a question.
Sure.
Yes, my question was that how do you combine the data acquisition, the 3D, in particular the cloud of points, with the geometric interpretation?
Excellent question.
Do you do it sequentially or just take first all the data and then you do the fitting, or how do you do that?
Excellent. So let me, so in some sense, it kind of starts here. This is kind of this is data taken from an RGBD camera, though we've done it with LIDAR and other kinds of sources. So when we get a frame, essentially what we're doing is 2 things. We're trying to estimate our orientation with respect to that. And then from there, we're trying to ask, well, did you see anything that looked like it could be a wall segment aligned along the X or Y planes? So at this very front end, we're doing a form of feature detection. You're getting these kinds of measurements to wall segments that you've seen. So by the time you get over here, you're already talking effectively at the level of objects. So you're saying that here are the various locations that I've been to, and at each location I have measurements to various wall fragments that I think I've seen. The tricky bit is this bit right here. These dotted lines are kind of where the magic happens, because it's all very well in a single frame to say, I think I saw a piece of wall, I think I saw a piece of wall. But what turns this into an overall interpretation is some way of saying, this wall that I saw at this time is the same as this other wall that I saw at a different time. And that requires us to hypothesize these links between the factors. And that leads to this model selection process that I would program, that problem that I was talking about. Does that help?
Yes, yes, thank you.
Okay. All right, so let me beetle ahead.
Now, hold on, one more question. Go back with one slide, one more slide, go back. You talk about predictive.
Yes.
So how can you do prediction if you don't know, if you haven't made any measurement?
Oh, that's an excellent question. So this is one of the many slides that I swallowed, but to my detriment. Let me see if I can answer that question. So here's one slide that kind of shows what's potentially going on. So remember that after I run this analysis, what I end up with is actually measurements of these infinite planes. So in this simple example, I have planes rolling on the X and planes running along the Y. So what these do effectively is they partition space into these cells. So I have these regions here in the world, and when I'm thinking about understanding this standing space, what I'm trying to do is hypothesize what these regions contain. Are they free space regions bounded by walls, or are they outside elements, or what have you? So prediction in this case corresponds to looking at these cells, which I predict because I discovered these various walls, and trying to guess as to what is going on inside them. So a good example would be that I see sort of two sides of a corridor, and I predict that the corridor is going to continue along this direction, even though I haven't necessarily got more data that goes down in that direction. Does that help?
Yes, I have been reading a lot of papers what the neuroscientists are talking about prediction. And it turns out that apparently in about 11 seconds before we make a decision, our brain is making this hypothesis, and then we actually do it. So this whole thing of prediction is apparently taking place in the cortex before you actually can observe the action.
Yeah, no, this entire question of prediction is actually something that's been really interesting me, and that's why
yes.
It shows up in this work. From our perspective, in kind of people that are thinking, if you think about it in the context, let's say, of that exploration problem.
Yes.
Concretely, our goal was to be able to sort of quickly survey an entire floor. So you want to do it kind of the way a human would. You want to kind of like stick your head in, observe a little bit about what's going on, and then use your overall understanding of the building structure to infer where the walls probably are. And so we've attacked it in this kind of very geometric way, but clearly there's been a lot of interesting work that's also done from a neural side as well. And I think that there's definitely fruitful work to be done in blending these kind of perspectives. So this is kind of exploring how far you can get by simply thinking about the geometry and using those constraints. Okay. All right, let me change gears a little bit and talk about some other work by another of my students, Chao Hu. And he's been looking at this problem of deep basis fitting. And this is actually, work inspired in part by stuff like CodeSlam and BANet and the like. Basically, what we're interested in doing is using a neural network to predict a low-dimensional manifold that contains the three-dimensional structure of the scene. And in our case, this is based on the image that comes in, as well as potentially sparse depth measurements. So one way to think about what's happening here is that it's kind of a contrast to what you would do with, let's say, a monocular depth prediction scheme, where what you're doing is you're giving your neural network this horrible problem, which is given a single image, predict a depth map for that scene. And what we're doing here is relaxing that a little bit and saying, okay, you don't need to give me a single depth map, but I'd be okay if you gave me a subspace that is likely to contain the right answer. So again, this is an idea that's been floating around recently. Our approach to it is a little bit different. So one way to think about that monocular SLAM problem is that you generate, if you look at the ultimate layer, there's typically a tensor or volume that then gets convolved with a one-dimensional filter, if you will, sort of a 1D convolution to produce the final depth map. And what we're proposing to do is actually replace that single convolution filter that gets learned with a adaptive piece that does a least squares fitting. So specifically, this is targeted at the problem of sparse depth, of upsampling from sparse depth. So it says, imagine that you have a world where you have some sparse depth measurements at some small set of, relatively small set of pixels. What I want to do is to regress those against a basis produced by our network, and use that to produce the final output. So perhaps it'll be slightly clearer with this image here. So this overall structure of our network looks something like this. So on the input, we have our image and perhaps some sparse depth. This gets fed into a encoder-decoder structure, which produces at the end a tensor. So think of this as, let's say, 64 images. And what we do is we have some sparse set of depth measurements over here, and these get fit against this basis to produce our final estimate. So the point is that this least squares fitting module is, well, first it can be stacked onto many networks that are proposed, so you can do kind of what you like in here, as long as you have this final output structure. And secondly, it's differentiable, which means that we can backpropagate through the entire thing to get the result. One small thing, but important thing I'll mention is that we found that it is important to have this nonlinearity here between the space in which we're fitting and the actual depth. The nonlinearity that we prefer is as a simple exponential, which ended up being kind of the magic that allowed us to get the kind of results that we were interested in. One side note that I'll mention is that in addition to being able to think of it this way, you could actually think of your basis as being done in a multi-scale manner. So kind of somewhat akin to what you would do with a set of wavelets. This turns out to be a very good way to approach it if you're interested in doing self-supervised learning. So we've actually demonstrated that we can apply our method to that as well. So it gives you sort of a course-defined structure. So what we did in these experiments is take a base network, one of the top performing ones, and simply add on our least squares fitting module to the end of it and do comparisons against the two. So I'm not going to ask you to sort of digest the entirety of it, but the take home of this table is that in all cases, our RGB, our least squares fitting module sort of substantially improved the quality of the results produced. It even did better when you're adding in outliers. So if you add in outliers, we actually have a slightly more impressive improvement over the baseline. And again, since this is a technique that can be applied to a lot of front ends, we've found that this technique actually holds up quite well. Another thing that was very pleasing was that we observed that when we did this, we applied this as a training methodology. Not only did it improve the results, but it improved the training. So here we're showing training results on both Kitty and NYU. And our curves down here are the lower ones, showing that it not only converged faster, but it converged much more stably, we found, by allowing the system to explore this, linear subspace, or generate a linear subspace that is being used to generate. This is an example of kind of using our system in practice. So again, you'd imagine getting a small number of points and then using them to upsample. Since we've been able to actually extend the method, so now we can not only just predict depth, but we can also predict uncertainty in our measurements by applying a Bayesian framework. So that we've actually been able to generate some very good results using that, which I'm not going to belabor. Let me move then quickly to the last thing I wanted to tell you about, and this is again some recent thesis work by my student Anthony Cowley, who just graduated, and he worked on a system called UpSlam. It's a real-time panoramic SLAM system. And our goal here was to actually overcome a frustration that we'd had with some of the LIDAR-based SLAM systems that we'd been working with. Namely, that we found that they were, in practice, or at least in our implementations, were a little bit fragile. So we've developed this other approach where the fundamental idea is actually quite simple. What we're going to do is represent our environment as a collection of panoramic depth maps. So this is not a new idea. This sort of this is an atlas-based representation. That's you will have seen it before in works by other authors. So the world is effectively this series of local representations connected by an underlying factor graph, which I'm not going to say very much about the factor graph other than it exists. To give you sort of the punchline, what we found is that these panoramic depth maps, if you think about it, sort of 2.5D representations, the underlying representation is essentially an array. And because it's an array, you have these very simple regular axis patterns, and that allows us to implement this projective ICP system very, very efficiently. And I'll show you some numbers about that. And lastly, the resulting representation is very compact and scalable. So it's a good way of actually representing large spaces. So again, there's other related work in this area. So for instance, by Malin, Comport, and Reeves, we've also done some similar things, though there are some notable differences. So first off, let me just one slide to give you an idea of what the underlying representation looks like. What we're envisioning is that at every point in time, the robot is maintaining a local map that might look something like this. This is a panoramic depth and associated panoramic normal. So 2D arrays is what you should think of. These panoramic representations are actually super resolved, so we actually have them at higher resolution than we get from our sensor and with greater field of view, but essentially it's a local panoramic representation. This video sort of gives you an idea of kind of what's going on. So we see our robot walking along, and every point you see one of these knots, it's one of these panoramic representations. And because there's an underlying factor graph, we can do things like loop closure and updating and all of that quite effectively. So again, the underlying representation is pretty compact. To give you an idea of the kind of problems that we were really interested in solving and sort of the source of our frustration. This is kind of give you an idea of the kind of data you would get from your average wheeled robot. On our bottom left is one of my favorite robots. It's a legged robot from our colleagues at Ghost Robotics. On the bottom right, you're seeing data that we collect from our flying platforms. And this is data from a human running around our building. So all of this data, it actually poses different kinds of challenges because the motion is different, the accelerations are different, the experienced twists and turns, particularly on this legged environment, are very different. But we wanted one algorithm that could deal with all of these kinds of data sets, which is what we ended up with. Let me see if I can give you an idea of what that looks like. So here, just showing you one example. This is mapping run on one of our graduate students' farms in Western Pennsylvania. This is a loop that was conducted. It's a couple hundred meters. And this is the resulting map that was gathered. Now, again, I want to remind you that this representation that you're seeing is not a single point cloud. It's multiple point clouds, multiple 2.5D representations that are simply just being unioned together to give you an idea of what this looks like. So to the extent that it looks like a continuous point cloud, it's because the registration is good. Because the underlying representations are much, much simpler than global point clouds.
Wow.
The other point I want to make here is to tell you a little bit about performance. So the sensors that we're using, they have a sweep time of 100 milliseconds, which means you get a new LIDAR scan every 10 times a second. On a regular 1080 GPU, we can process a single scan in 4 milliseconds. And when I say process, I mean use every point in the scan. We can process it at that rate. So 25 times faster than we're getting it. We've also gone and implemented this on embedded platforms. So NVIDIA Xavier is one such platform. So here we get cycle times on the order of 15, 20 seconds, but we're doing this on platforms that are using 15 watts of power. So we can now be talking about implementing these things on things that are small, that can be battery constrained, but that still need to run at very, very high rates. And again, this is down to the fact that our underlying algorithms really are highly parallel because of the way that they're structured. In terms of accuracy, we've done comparisons against data sets. I'm not going to terribly belabor this. This is the newer college data set at Oxford to give you an idea of the error that we're getting over this entire trajectory. And this is the two trajectories overlaid upon each other. And now I'm just going to show you, gratuitous use of videos. Again, to give you an idea, we've tried it on data from flying platforms, from these legged platforms. This is the newer college data set in Oxford. The other thing that I'm not telling you about is that there's another complete story about visualization. So Anthony has this really cool way of turning these panoramics into truncated signed distance fields, which allows us to do rendering with full occlusion. We can do transparency. We can do a lot of things that you wouldn't necessarily think are possible with just this simple array representation. But and by the way, this visualization also runs in real time. This is not sped up in any way. Here's an example of us running on this extended data set that we captured from a car. I'll show you a little bit about what that looks like. And this is just sort of giving you an idea of what so definitely not perfect. But what I would ask you to remember is, again, all we're doing here is representing the world in terms of a couple of arrays. In this case, it's 1,045 arrays spread out over a couple of kilometers.
Now, Camelia, what you have shown is this is just a pixel or voxel representation, or did you also smooth it into some geometric representation?
Excellent question. So again, the fundamental representation at the base of this is really, if you think about it, just a series of these 2.5D panoramic representations. So they're just arrays.
So it's points, basically.
Yeah, so the way to think about it is that you have this set of local maps. It's literally an atlas. But each of these atlases is a very, very simple thing. It's just a 2.5D representation. But that 2.5D representation, I argue, is nice because it Well, first it allows you to capture a lot of the free space that would be very, very difficult to capture in something like a voxelized representation can be captured very effectively. The other thing is it provides, and again, we're getting into a little bit of inside baseball here, but since each of these representations is essentially 2D, you can use the topology of the image to do smoothing on. So something that I'm not saying but is very important is when we do things like finding normals and we can do that very effectively because there's a natural neighborhood structure to our representation. So we can do things like smoothing. We can do things like filling in holes because of the way that our representation gets structured.
Well, my concern is that this is okay for visualization, but if you really want to decide that whether you have a plane or whether you want to act upon this data.
Yeah. Oh, excellent question. So I would say two things. This is actually a little bit related to the first thing I talked about, where they're also, if you think about what we were getting as input, they were effectively depth maps. So what we're talking about here is a way of collecting local representations together to form a much better local depth map. And from there, you can do things like if you're interested in finding surfaces or planes, you can do that in this representation. The other kind of obvious thing that you can do here is you can attach semantic data to this. So this is something that I did not talking about, but we've already done. So we actually have semantic versions of these representations where we can now reason about what's happening in the local scene structure. And we've been using that for a couple of tricks, which I will mention if you twist my arm.
Okay.
But let me just conclude then. Don't want to try your patience anymore. So what I'm arguing is that this atlas-based panoramic representation is helpful, I would argue, because it allows us to represent local structure quite accurately. So if you look at an individual panorama, you can, if you're close enough, be talking about stuff on the order of centimeter or even sub-centimeter accuracy in a local representation. So if you're thinking about tasks like grasping stuff on a table, you can do that. There's enough detail in these local representations. But on the other hand, it allows us to scale. So now we can represent things on the order of a city because each local representation is very, very small, very compact. So that data set that I showed you over there, the entire town fits in 1.2 gigabytes on disk. Even though the underlying data that was coming in was many, many times that in terms of raw computation. The other point I would make is that our representations are simple, but I argue that that's actually an advantage.
Yes.
Because simple means regular means fast. And because we're able to process things so quickly, we don't have to make hard decisions early. So if you contrast us with methods that are trying to do feature extraction early on, we don't have to do that at all. We use all of the available data in the scan to help us solve the SLAM problem. And I would argue that that is what allows us to deal with kind of the multiplicity of environments that we've been able to test this system on. So I guess I'm going to leave it there since I see we're 10 minutes past 8 and I've tried your patience enough. So
thank you very much.
Thank you so much.
Yeah, go ahead, Caroline.
Oh yeah, thank you so much. I'm going to stop the recording right now.